Today, we are tackling a seriously powerful tool that engineers use to cut through the chaos of circuit analysis. It's called the Laplace transform, and believe me, it's a tool that can take a mathematical nightmare and make it, well, surprisingly simple.
So let's get real. When you're analyzing a circuit, you often end up staring at something like this on the left, a tangled mess of calculus. I mean, who wants to deal with that? But what if there was a way to just magically change that entire problem into a simple algebraic equation, like the one you see on the right? Well, that's exactly the shortcut the Laplace transform gives us.
Okay, so to really get why this shortcut is such a big deal, we have to start where the problem begins. And that's in what engineers call the time domain. This is basically the real world, right? It's where we describe how voltages and currents are changing over time. And as you can probably guess, the math here can get pretty gnarly pretty fast.
Yeah, the equations we use to describe these circuits have a fancy name: integral differential. All that really means is that they're a mix of calculus's greatest hits, derivatives and integrals. And when you mix those two, trying to find the complete response of the circuit, the whole story of what happens from the very beginning to the very end, is just incredibly tough. And this is exactly where our hero, the Laplace transform, swoops in to save the day. The best way to think about it is like a portal. Seriously. It takes our complicated calculus problem from the time domain and, whoosh, it transports it to this whole new world, the S domain, where the math is refreshingly simple. So what's the game plan? Well, it's actually a super clear three-step journey. First, we use the transform to jump through that portal into the S domain. Step 2, we solve the problem there using just simple algebra, no calculus. And then step 3, we use something called an inverse transform to bring our nice, simple solution back to our world, the time domain. Now, the whole point of this, the primary goal, is to find what's called the complete response of the circuit. And that's huge. It means we can predict everything, not just the final, settled state of the circuit, but also that initial, often chaotic behavior that happens right after you, say, flip a switch. That's the transient part, and it's super important. Okay, but before we can even think about transforming anything, we need a way to talk about those abrupt changes in the language of math. I mean, how do you actually write down a power source suddenly turns on in an equation? It's a good question, right? Well, the answer is something called the unit step function. Just imagine this, a signal that's totally off, 0, for all of time. Then, at the exact moment we decide it's time 0, it instantly flips on to a value of 1 and just stays there forever. It is the perfect mathematical model for flicking a switch. And to handle the math behind such a sudden change, we have another cool tool on our belt, the unit impulse function. Now, this one's a bit more theoretical. Think of it like a jolt of infinite power that lasts for 0 time, kind of like a tiny perfect lightning strike. But the real magic for us, its Laplace transform is just the number 1, and that makes our algebra so much cleaner. All right, so let's check out the rules of this new SK domain. This is where we really get to see how that portal works its magic. And honestly, this is where the true power of the transform becomes crystal clear. Okay, check this out. This is the heart of the whole thing, the real magic trick. Over on the left, in the time domain, we've got those messy calculus operations, differentiation and integration. But once we step through that portal to the S domain on the right, bam! Differentiation just becomes multiplication by S. And integration? That just becomes division by S. Just like that, calculus is gone. It's just basic algebra. And here's something that is a massive advantage. You know the circuit's initial conditions, like the voltage that was already on a capacitor or the current already flowing through an inductor before you flip the switch? Well, all of that is automatically baked right into the new algebraic equations. You don't have to do any extra steps to account for it. It's just there. All right, so we did it. We used our portal, we solved the problem with some easy algebra, and now we have an answer. But wait a second, it's still in the S domain. It's like we've got a souvenir from another world. We need to bring it back home to the time domain so we can actually understand what it means. So this return journey, it follows a pretty standard recipe. Our answer from the S domain usually looks like a fraction with a bunch of variables in it. So we use this technique called partial fraction expansion to break that big, clunky fraction down into simpler, bite-sized pieces. And the great thing is, each of those simple pieces has a known translation back to the time domain. So we just piece them all back together to get our final answer. But hang on. A solution on a piece of paper is one thing. As an engineer, you always have to ask the big question. Does this math actually match reality?
You know? Does this answer make any physical sense in a real live circuit?
Thankfully, we're not just guessing. We have two really powerful theorems that act like a reality check. First, there's the initial value theorem. That lets us calculate what's happening the instant after a change happens, checking our immediate response. Then there's the final value theorem, which tells us what the circuit looks like after a really long time, checking that final steady state. It's kind of like peeking at the first and last pages of a book to make sure the story tracks.
So, when you put it all together, what's the big payoff for doing all this? Well, we get the complete response, the initial spike, and the final settled value without all the headaches of calculus. And all the starting conditions are handled for us automatically. But the most important reason we do this, it's a very practical one.
And this, right here, is the absolute most critical real-world reason to use this. This is not just theory. That transient part of the response we talked about, it can show us these huge spikes in voltage or current right after a switch gets flipped. And knowing how high that spike goes lets an engineer make sure it doesn't go over a component's maximum rating and, prevent it from literally blowing up. This is all about designing circuits that are safe and that actually work.
So, in the end, the Laplace transform teaches us a lesson that's way bigger than just circuit analysis. It shows us that sometimes the best way to crack a really tough problem is to completely reframe it, to find a portal to a new domain where the solution is simple, and then just bring that answer back. And that kind of leaves us with a bigger question, doesn't it? What other complex problems out there could be simplified just by looking at them from a completely new perspective?